I appreciate for those of you who filled it out. Also, again, if you didn't take the quiz, again, you find it over here. Just take it. I think it's open until September 20th is what I said, but honestly, if you take it by the end of the week, please, if you want your 5 extra credit points. So it's just going to be over here under quizzes. Now, with regards to the what we're going to do today, first I'll just simply drop a link to it in the Discord. Just in case, if you're already on there, you can have it easy access. Otherwise, you can easily find what we're doing today by going to modules, and then the module 2 overview, and then clicking on the link at the bottom over here that says Thursday will be a longer exercise, right? That'll bring you to the same link that I just dropped in course, or finally, third way, you can just simply go to, Runestone, go to our textbook, go to the textbook, scroll all the way down, and considering we've done projects 1 and 2, you probably have a good bet as to which project this is. I mean, you learned how to count, I'm pretty sure. I'm pretty sure I learned how to count. I think I did. All right, anyway. But today's is input, compute, output. And it's about a series of really annoying questions that used to get asked at programming interviews that are testing for something that really isn't taught at school, which is a way of thinking flexibly. It is learning about how to do really freaking large computations without them being too scary. So there's basically 2 important kind of ideas here for when we encounter really large problems, which is that we got to make our assumptions and we got to write down what our assumptions are. We'll see that in a bit. And then solving a problem by generalizing them from a simpler version of that same problem. All right? Solving a problem by generalizing from a simpler version. So we also do, and the way we solve these problems is also through using another method another computational model or pattern they call it, called input, compute, output. In other words, ask the user for input, compute something, give them the answer. This is what a lot of Lab 2 is about, right? Input the number input the parameters, give you the amount of chocolate you need to stay alive if you're just staying in bed. Calorie-wise, the nutrition ain't going to be that good. Input the temperature in Celsius, and get me the temperature in Fahrenheit. Input the number of seconds, give me the amount of hours, minutes, and seconds that is. Right? That's input, compute, output. Okay? An example of this is here in this code block over here. Enter a number of years, and I'll tell you. So here we've got an input statement asking for the number of years, and I'll tell you how many minutes that is. And then we convert that number of years in that string. We do a conversion here. Int years is equal to years, which is weird if you haven't seen it before. But what we're doing here is that this input gives us a string. It gives us text. And we store it in the box and labeled years. Then we say, I want to take what's in the box labeled years, convert it into an integer. That's what this int function does. Convert it into an integer and store that in years instead. Okay, can't store more than one thing in a box. Just this, we're taking out what's in the box here and putting it and converting to an integer and putting it back in. Right? The idea. Okay, so now the reason we're converting it to an integer or a whole number is because we're about to do some mathematical operations we're about to do some mathematical operations to compute how many seconds that is. Minutes that is. And we can't do mathematical operations on strings, or at least we can't do them and get the results that we want. So the idea here is that this program, run it, given the number of years, like 5 years, it will tell me how many minutes that is. 5 years is 2.6 million minutes, which is both seems like a lot and not that much at all, right? Because minutes are pretty short. Okay, so how do we do this kind of computation? Well, what we do is that we convert. We say, okay, I don't know how to convert years into minutes directly. What do we know? We know how many days are in a year. Kind of. It's complicated. It really is complicated. So we take years, we multiply that by 365. We'll just use 365, even though the real number is not quite 365.25. Not quite there, but it's close. So 365 should give us a relative amount. That will tell us how many. That will give us how many days, right? There's 365 days in a year. So we take the number of years, multiply that by 365. That's how we get to the number of days. We then take the number of days we have. There's 24 hours in a day. So if you multiply the number of days by 24, this gives us the number of hours, right? If it was 1 day long, then it'd be 24 hours. If it was 1 year, we would multiply that by 365, then take that 365 and multiply that by 24. Then finally, we take the number of days. So once we have the number of hours, we can convert from hours to minutes. Okay, hours times 60 gives us the number of minutes, and that's our answer. We can print it out very simply. Does this make sense to everybody? Where we go from, this is what we need to do step by step. But now you've seen it, it's kind of fairly straightforward. So now let's take a minute, and instead of doing this from years to minutes, try years to seconds. All right? Try going from years to seconds. So you can add on to this code. You don't have to start from scratch. Modify this code, right, so that we can go from years to seconds. And I'll get you started in case you're like totally terrified about what to do, right? What you want to do is you want to follow the pattern. Add seconds is equal to, and then change this down here, the print statement, so that it becomes seconds, so we get the right answer, and change this to seconds. And this shouldn't take more than a minute, not too much. Yes. Sorry? The number of seconds in a minute. Right. Did you remember to change this? Right, let's try that then. What you should do to get the answer is take the number of minutes and multiply that by the number of minutes that are in seconds that are in a minute. So we had about 2 million over here. So if I do 5 years, I should now be getting, I get hundreds of millions. 5 years is 157 million seconds. So years, days, hours, minutes, and that gets us to seconds. All right. Now, of course, can you go the other direction is the question, which is change the problem to go in the other direction. Given the number of seconds, how many years is that? Well, we've got two ways to do this, which is the one is the cheating, what is a bit of a cheat, which is I'm just going to go ahead and figure out okay, a year is this much, and then I could copy and paste. Otherwise, another way to do that is we can say, okay, seconds is equal to input, and I'll just be very succinct here, enter num seconds. Seconds is equal to, because again, we're going the other way now. That's the task right now. Seconds is equal to seconds, int seconds. Okay, and now we want to figure out how many years there are in that. And we're going from a smaller unit into a much bigger unit. So in this case, we want to turn seconds into years, so we have to divide by some number. Now we could use that number that I popped up on the screen. One way to do that, though, is that we can do seconds is equal to, so in other words, years is equal to seconds divided by what? What should we put here? A lot of different things we can put here. Well, how many seconds are in a, well, we kind of can go in reverse. Seconds in a minute times times 60 minutes in an hour, 24 hours in a day, 365 days in a year. Let's go ahead and, I'm going to go ahead and take that and print it out. Just to make sure that I've not gone crazy here. Okay, and print out that. Okay. And what is this string of numbers I put out here? That's the same, well, as it turns out, it's the same string of numbers that I got when I put in 1 year. What I did is that I calculated how many seconds were in a year without actually writing it down. I just simply said, okay, there's 60 seconds there's going to be 60 seconds in a year, right? Again, a way I could do this would be, so this is one way to do that. Another way I could do that is I could go minutes is equal to seconds times 60, days is equal to, sorry, not days, I skipped ahead. Hours is equal to minutes times, let's see, so divide. We're dividing now, not times. Number of hours, divide by 60. Number of days would be hours, divide by 24, because there's 24 in a day. And then years becomes days, divide by 365. Everybody following so far? How this number over here and this calculation ends up being the same? And we can print that out now by saying, okay, so let's go ahead and comment that out, and instead I'll print out the years. So, and I'm not going to bother writing the fancy inputs, the fancy output statement for it at the moment. So let's go ahead and enter 1 billion seconds. It's about 31 years. Which makes sense given that we had 5 where we did. Where we had 5 seconds equal to what? 10 billion? So we'll see. So, and remember, so one thing to keep in mind though while we're doing this calculation is that I'm doing there's a lot of bits that go missing here. What do I mean by that? Well, right, we chop off extra seconds here, we chop off extra minutes here, we chop off extra hours here, and we chop off extra days here that don't fit cleanly in. If we actually do actual division, we'll get a slightly different number. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. And we get 31.7 billion. 31.7 seconds. 31.7 years is what converts to 1 billion seconds. Okay? Now the last part of this is enhanced part 2. So you can print the number of years, months, days, and minutes. Now, we could just simply print out like it's equal to... Now, I'm always confused as to what the directions actually wanted me to do here. Are they saying that I want to say that seconds is, and here you'll see what I'm doing, print minutes, comma, minutes. So we'll take a look at and explain the print statement in a second. Minutes, comma, or print hours, comma, hours, comma, or, and then you kind of get the idea going on where I'm printing out each individual unit as it's been converted. So like, again, if I answer in a billion seconds, it's this many minutes, or this many hours, or it's this many years, this many days. Or is it saying it wants to convert it to it's 31 years, this many days, this many hours? Does that sound familiar to anybody? Yeah? The lab. So, in one of the lab questions, we're asking convert days into seconds. Sorry, not days. Seconds into hours. So if given a number of seconds, like 5,000, I think it was 5,000 seconds is 1 hour, 23 minutes, and 20 seconds, I believe is the input and output. I've had to test it a lot, so I've got that memorized. So how would we go about doing that? Well, what we'd want to do is not start with the smallest unit first, ironically enough, but the biggest unit here, which is annoying. So if I want to figure out how many years this is, made up into a second, I'd take this number that I have over here, the 60 times 24 times 365, and if I put in a billion seconds, that's going to give me 31 days. Sorry, that's going to give me 31 years, right? This will give me 31 years. But then I have the 0.7 that's remaining, right? The 0.7 left over. And that's what needs to get converted into the number of days. Make sense to everybody? Right? So this gives me, how many years. And then this part, I'm going to call it leftover, or actually, let's call it what it is mathematically. The remainder, the leftover seconds, will be seconds mod, and then we're going to take that and copy it. It's the seconds that don't fit into a whole number. Right? Number of seconds that don't fit into a whole number. Right? So that gives me that. And then what I can do is, okay, well, the next step is figuring out we figured out how many years. So how many days do these leftover amount of seconds comprise? And the answer is this. Well, we say days is equal to not seconds, but what we have for us the remainder divided by, and there's 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day, and that's all as far as we need to go there. right? So notice I just simply drop this part. And then and that will give me the whole number of days that are left, right? And then to do the remainder, I just simply use modulus again. I say the remainder is equal to the remainder mod 60 times 60 times 24. Now this line I probably combined some of the most confusing stuff that we've seen so far. Let me go ahead and open up idle for a second, because that's about as far as I'm going to go into this. Because if I go any farther, I'm essentially done the last part of lab 2 for you. But if you're following along, this should give you the tools you need to do the last part of lab 2. Okay, not lab 4, but fourth part of lab 2. All right. Part of what students have struggle with is this. X. Let me go ahead and increase the size here. File. Let's see, because I want to configure font 25. Yeah, I want it in the 30s. 34. Okay, there we go. X is equal to 5, right? No problem there. If I print out X, it's going to tell me it's 5. This is what gives, so now, if I say y is equal to x, this simply says, hey, take the value in x, copy it, store it in y, right? No problem. If I print out x and y, it's going to give me 5, and y is also going to be 5, okay? Now let's look at aside from for loops, this is what students struggle on the most. X is equal to x plus 1. Now this statement is completely invalid in mathematics, right? If you're trying to solve an equation in mathematics, and if you end up with this as your equation, this is an indicator that something's gone horribly wrong, right? That you did your algebra, you messed up somewhere, right? But you got to remember two things. First off, this is not an equation. On the right, we have an expression, and this is an assignment statement. This says, do what's on the right and store it on the left. So remember, it says it's an equal sign, but in reality, it's a big arrow, like that. Okay? Which means that this is saying, take 5, add 1 to it, and store the result in x. And as we all learned very early on, 5 plus 1 is 6, right? We're not going to be doing any crazy math here. If you see any crazy math here, it's always a trick question, okay? So I enter that, I hit slash by accident, oh well, x, and x is now 6. Now this is the important part. What is y? Yes. 5. Yes, it's 5. It's 5. Because I said something key earlier. We take what's in x, and copy it and put it in y. So y has a copy of what the value is. So the variables are not strongly linked. Changing one variable is not going to change another variable. Vast majority of the time, when we get to objects, it's a bit more complicated, but you'll understand what I mean then. The reason for this is because human brain dumb. That's why. Human brain dumb, can't remember much. Think about how complicated it would be if you had to remember if you changed one variable, if you set this equation, and then you changed x, and then you'd have to remember about y every single time. Right? You'd have to remember that any change to x would also affect y. That would be just so complicated when you've got like 20 variables running around, right? So no, the variables don't get strongly linked with each other. So changing one variable is not going to change another variable. It's just not. Okay? Remember, this is an assignment statement, and this says compute the result on the right and store the result in the left. Okay? So when I say this over here, when I say remainder is equal to remainder mod this value, what I'm doing is I'm taking the original remainder, dividing it by a big number, taking the remainder, and overriding the previous value there. That's what's going on there. So I'm overriding the previous value. I don't have to do that. I could like do remainder 2, but why? That would be a that would just create another extra variable. I'm going to go ahead and save this, even though it's going to crash. I'll go ahead and share it with you so you have it for future reference. And I will also share the previous one with you so that you'll have it for future reference. All right. Got a good 40 minutes left. It's fine. So there used to be a bunch of questions that got asked about in computer science interviews that weren't really indicative of programming skills, but rather indicative of something you wouldn't be taught in any class at all, which is gross estimation, as well as critical thinking skill, as well as just some critical abstract thinking skills. Some of them were annoying, like why are manhole covers round, which has a lot of reasons, you know. It's a kind of classic one. Or, although this one was another one, how heavy is the Empire State Building? Or, you know, how many or to keep using Manhattan as an example, how many houses can fit on Manhattan, on Manhattan Island? Or another one, how many gallons of water come out of the Mississippi River Delta per day? These are not questions that you can have an answer to. You cannot. They're mind-bogglingly huge numbers for one, and you really normally aren't given kind of tools to equip it. They're open-ended. And because they're open-ended, that actually is the point of these questions. You don't know, they're open-ended, so it's up to you to come up with a strategy to solve them. For example, estimating how big you remember what I was saying earlier about writing down your assumptions? Let's take the Empire State Building again. Okay, Empire State Building, how heavy is it? Well, how much does the house weigh? Make a gross estimate of that. Probably a bunch of tons. Figure out, so pick a number. It's probably wrong, but that's easy enough to adjust. Anybody? How much does a house weigh? 20 tons. That's what I was going to pick. 20 tons. That's probably on the light side too, I would guess. I have no idea how much stuff weighs. I'm not a construction person, but hey, I picked a number now. That gives me something solid. Okay? Now, think about how tall and how wide a house is. Think about how big is the Empire State Building? How many houses could we fit across a single floor? And then how many floors are you going to guess that it has? Now you have a strategy for getting an answer that will at least be somewhere in the ballpark of the right magnitude. Similar with the Mississippi River. How wide is it? How fast does it move? How many gallons does that come out to? You're not supposed to know the answer. What these questions were looking for was, would you freeze up, or would you actually just try to start making an approximate answer to this question? So this one's going to be fun. So we're going to do one in class today, which is actually not so bad. This one is for and if you're from the West Coast, you might appreciate this. How many trees are in the state of Washington? Not Washington District of Columbia, but the West Coast, Washington. Right, Washington State. Now, is anybody here from Washington? No? Anybody from the West Coast in general? No? Really? Go figures. Well, you may not know, but the further out west you get, the more loosely populated the United States is until you get to the coast again. And that means that there's a lot more open area. In fact, let's go ahead and open up a map, right? Let's go ahead and open up a map in a private browser so I don't accidentally dox myself or something like that. All right, and let's go ahead and look up Washington State. All right. Ooh, okay, and it gives us quite a bit of information. All right, so this over here, this outlined area here is Washington. And we can see that basically there's a lot of forest in it. A lot of forest. How much forest would you say Washington is made of? Percentage-wise. Yeah. 60%. What were you going to say? 60? 60%. Anybody was going to say 50%? Yeah? Yeah, 50, 60%. Doesn't really matter. 40, somewhere between 50, 60, 70%, I would say, right? It really depends. I mean, you get more of a view of it if you switch to satellite view, right? You can really see. And there it kind of looks maybe a bit more 50-ish, right? Again, it depends on what kind of data you're coming in with, right? But it's pretty forested. So now that you know, okay, half of this looks like forest. Not trees, but forest, which is different, right? There's still going to be trees in all this area, right? Tons of trees all here. That looks like that's got plenty of tree, although that's farmland. But you also know that cities got trees in it, but the vast majority of your trees are going to be in these forests. So about half of it is in forest. So how many trees are in a forest? Or better yet, what's a better question? Yes?
Well, you kind of talked about trees not being forests, so how dense are trees?
Yeah. How dense are the trees in a forest? That's a pretty good way. Not all the trees are going to be in a forest, but we can kind of just ignore them because the vast majority of them are going to be in the forest, right? So, how many trees in a forest? How about per acre? How many trees in an acre of forest? That's something to use as an estimate. All right. So, what I want you to do is work with some group members. Just people around you. Feel free to work by yourself as well, but you can work with the people next to you and kind of just take a look at figuring it out. There's no exact answer here. There are just simply different orders of magnitude based off of different estimations. The fun is figuring out what your assumptions are. So go ahead, take 5 to 10 minutes to work on it. Use this widget over here, this window over here to help you as kind of a calculator to help you write out your thought process. One advantage of using variables is that helps you remember how you got there in the first place. Recording again. All right. So does anybody want to share their answer? Yes. Either of you. One of you speak. All right. 9,900 trees or? That is, so how did you get there? Because I want to know what your calculation is.
Okay, so from the area of Washington,
Uh-huh.
then the forest is about 1/6 of that,
Uh-huh.
and then we converted that to acres.
Okay.
And then we did average number of trees in an acre, like a forest.
Okay. So you have the right idea. You must probably divide it somewhere when you needed to multiply. Yes. 3 billion trees. That's more of the order of magnitude there. All right. Anybody? What about anybody else? And how did you get that?
So I just looked up and said there's about 100 to 200 trees per acre of forest.
So let's. So trees per acre. Let's call it 150. And then how many? And then how many acres? 22.5 million for Washington. 22.5 million, so let's call it Washington acres, and that's just total acres, right? So 22 million acres is kind of the idea here, right? 22 million acres in Washington about. And then percent trees is equal to 0.6, right? We kind of estimated that that maybe 60% of the place is forest. So what we'll do is we'll take all three of these numbers and we'll kind of multiply them together. Trees per acre, right? And you could get different numbers based on whether you look something up or you made a different guesstimate or whatnot. So trees per acre, we assume that Washington has this many acres in it, and then we multiply by the percent trees, which was 0.6, to get the total amount, which was, because again I'm using slightly different numbers now, right? But I get 1.9 billion, about 2 billion with that amount if I round up. Anyone else? Anybody get into the 10 billions order of magnitude? Anyone? Yes, back there.
I got 428,172,000 trees.
And how did you get that?
There's 71,362 square miles in Washington.
Uh-huh.
60% of that is trees, and the website said about 10,000 trees make up a mile in forest.
That's an excellent way of doing that. 10,000 trees per square mile forest. Yeah, that's easy to remember. That's nice. Nice clean number there. Unless you're not American, in which case you're much more familiar with kilometers, which is a much more sensible system, unfortunately. Sorry, we use imperial units, or as we sometimes call them, freedom units. Anyway, but regardless, the idea here is that everybody will get slightly different answers. Some of you get hundreds of millions depending on what you have. Some of you get 10 billion. Some of you get billions. A lot of people end up in the billions range. Yes. Yeah, 3 billion is 1 to 3 billion is a pretty common mark here.
Like a tree acre density, Washington State, like 65.7. So then you just multiply by the amount of acres.
Yeah, it's a good way to do it. So again, it's a matter of even though a problem seems insurmountable, by breaking it into these parts and thinking about it, that's how we get to an answer. One of the most common themes in the courses that I teach is that things are always a lot easier than they appear to be at the first glance. For instance, you'll get your first really good taste of that when you do the Hurricane Tracker program at week 7. That one will really show you, actually, when I break it down into these tasks, this isn't so bad. Now I do most of these homeworks myself before I assign them. If it's not trivial, I gotta do it myself to make sure that I can get an estimate about your time. It took me about 3 hours the first time to do the Hurricane Tracker. And the reason is not because I made a programming mistake. This is a mistake you'll be able to benefit from, but because because I forgot, wait a second, latitude and longitude. I forgot to figure out which one goes to X and which one goes to Y. So when you get to that one, I'll mention it again, but make sure you're putting the right one in X and the right one in Y, because otherwise your turtle's going to be off the screen somewhere doing his own thing. All right, so how many so this is another one. Rather than doing a kind of computation there, what we're going to look for is a pattern. Now this is a pattern that I kind of have an advantage on because, I don't know, it's been burnt into my mind now. So, how many handshakes would it take for everyone in your class to shake hands with everyone? this was a very interesting question to ask, in fall of 2020 when we were all online, since that would require, not being in Zoom and breaking a bunch of health regulations at the time. But again, the idea here, though, is that you don't shake hands with any person twice, and you're not shaking hands with yourself, right? You don't shake your own hand. So the idea here with these kind of problems is to start small and see if you can't find a pattern, right? So what if the class is only 2 people? What if it's 3 people? What about 4, 5? Let's go ahead and, now in these kind of cases, when you're drawing these kind of things, we're actually going to draw it out and on a whiteboard for a second. Okay? Now, I normally have a pen for my computer, but I don't have that with me because it's still lost somewhere in my luggage. So I'll find that eventually. All right. So the idea here is we've got this. So now for people, so there's this term here that you're probably never going to hear again, but it's called metasyntactic variable. Meaning it's the name that we give things to use as variables. So often you use x, y, z in mathematics. You use t for time. But here, like in computer science, we typically use things like, the most typical variable names you'll see in computer science are foo and bar and also baz. That's what you'll see in American computer science. Other languages have their own metasyntactical variables, but I have a feeling this one comes from the amount of kind of overlap between the military, because if you have that background, you might know what foobar means, which stands for something that sounds that doesn't sound like fouled up beyond all repair. So, but anyway, those are the typical ones that we use for computer science. In security questions or in computer security, when we're talking about 2 people wanting to talk to each other, we typically talk about person A and B, and because person A and B is boring, we instead use Alice and Bob. So that's why we'll be using Alice and Bob as often as our examples. That's why you'll see them so a lot. So in a class with just Alice and Bob, A and B, there's just going to be one handshake to make. Right? If we add Carl into the mix, see, Carl has to shake hands with Alice, Carl has to shake hands with Bob. 1 + 2. Now let's add Dan into the mix. Right? In fact, we can do a bit better. We can still make this graph planar, which is a fancy way of saying that we can draw this without having to overlap any lines. 1, 2, 3 + 3. So we can add in another 3 there. So with 4 people, we can add, adding a 4th person adds 3 more handshakes. Now if we add E for Edgar, we are going to, Edgar would have to do 1, 2, 3, 4 handshakes, right? And anything beyond this gets extraordinarily messy. But with this, we can see a pattern. If we add the nth person, then that adds adds n minus 1 extra handshakes. Now, a bit of mathematics here, and a bit of actual hints in future math classes for you. So the first pair gives you this, the second pair gives you this, the third pair gives you this, 1, 2, 3, 4, and then we would get 5 from adding a 6th person, right? So adding the second, then the third person, then adding the 4th person, then the 5th person, and then the 6th person. We can arrange this kind of the amount of additional handshakes that are required in a triangle. In fact, this sequence, 1 + 2 + 3 + 4, is called the triangular number sequence, right? Or the numbers that result from it, right? The numbers that result from it being 1, 3, 5, 9, and then 14 over here. This is triangular numbers. And for those of you who have taken Calc 2, anybody here taking or taken Calc 2, right? You have to deal with convergences in that class, right? So get very familiar with this equation if you're taking Calc 2, because you'll almost be guaranteed to be asked about this. 1 plus 2 plus 3, dot, 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 all the way to n minus 1 plus n. Right? And you'll be asked, what does that equal to? And part of what they'll teach you in Calc 2 is via induction, that actually has a nice, very simple equation there. Okay? Which is n times n minus 1 over 2. Now, there's a proof for it, but a lot of you aren't there for, I'm not teaching this math class here. If you're getting into 2168 or 3223, I'll be happy to teach this to you. But the idea here is that we have an equation. Or something close to it, because technically, if we have n people, we're adding this n plus, we're only adding this bit. If we have n people, then we should add this. So really, it should be n minus 1 times n minus 2 over 2. But we'll see in a second that we have an equation for this. This is what the pattern ends up being. Enough trial and error will give you that pattern, by the way, being able to write an equation. But knowing that there are sequences out there that come up again and again and again and again. This one shows up all the time in computer science, the triangular number sequence. So how many does it take to input? So how many handshakes for all the people in your class? Well, we can solve this I'll show you how to solve it using the equation, and then I'll show you, but I'll do that after I show you how to solve it using brute force, using what will be the topic of next week's discussion, for loops. Okay, num people, and let me go ahead and make this bigger. You can make these windows bigger, by the way, by just clicking this corner and dragging as much as you want. Okay? Now, num people, I swear I passed 4th grade. I know how to spell. Okay? Num people is equal to input, enter number of people, right? And then if we do num people, so first off, we want to always convert this back into an integer, right? This is just text, meaning that it's as valid to insert numbers here as it is to insert the word apple, right? But we want to make sure that we don't enter the word, we don't want to make sure we're not doing math on a word like apple, so we're going to take what we have, convert it into an integer. If they entered in stuff that is not good, which I'll show you in a second, it will crash, right? So if I put in, but this converts it into a number. So here I have the input statement, enter the number of people, and then if I put in 10 apples, in your 10 apples, once I run it, it will give me error, invalid literal for int with base 10 apples. So if you parse that, it's basically saying, I guess that you can't convert letters into a base 10 number, right? So there you go. So number of people. So anyway, we have the number of people, right? So the idea here is that we can use a for loop over here for I in range, let's say, so let's see if we can, so this takes some adjustment. Let's see. Handshakes is equal to, so this is a common pattern we'll see called the accumulator. I'm not going to do 5 there. Instead, I should do num people, and I'll put in 5 instead. For I in range num people, let's see, 0. So if I put in 2, that's going to be 1. Yep. So that's what I want. Handshakes is equal to handshakes plus I. Okay, what's going on with this statement? So first off, handshakes plus I, ignore what I is for now, just know that it's going to be some number. Okay, I'll discuss what it is in just a second. I is going to be some number. What we're doing is we're saying take the current value of handshakes, add I to it, and replace and update handshakes. This is called the accumulator pattern, where basically where we start at 0 and we keep adding a number to that pile. So like if you're trying to, if I were to go across and ask everybody for a number and add them together, that would accumulate. Yes?
Don't we have to subtract 1 to get rid of the single handshake?
It shouldn't.
Handshake with yourself.
It shouldn't because, I'm going to double check. That's why I do this. It shouldn't, but I think this should work. You shouldn't need to subtract 1, but what we might need to subtract 1 from is the number of people. Pancakes is equal to, why did I say pancakes? I'm thinking, obviously I'm hungry. Print, this is what happens when you type and talk, by the way. I think what happens is I started typing print and started for handshakes, and so that became pancakes because that was the only thing that I could possibly turn into. Okay, print handshakes. So there you know what goes on, what awful thoughts go on in my heads. I think about pancakes, I guess. All right, so enter the number of people, 5. That should give us 10. So let's see, 1 plus 2 plus, 1 plus 2 plus 3 plus 4. 1 plus 2 plus 3, 4. That gives us 6 people. So I think I did my math wrong earlier then. Let's see. 1 plus 3 plus 5. Yeah, 1 plus 2 plus 3 plus 4 should be 9. Let's go ahead and see for, and now let me go ahead and try for 6 people, which will add 5 as the last one, so that will give us 15. So yes, you're right, we do want to subtract 1 for the shaking of ourselves. Right, we don't shake our own hand. And let's see, save and run. If I have 6 people in class, there's going to be a total of 14 different handshakes. Hey, that seem right to everybody? Let's go ahead and double check. We've got 5 people in class here, so 1, 2, count the number of edges. That's what the lines between the circles are called. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. So adding a 6th person would connect 5 more lines. Yes? Have an extra one? Aha! That's where the 10 came from, I'm sure. That's easy enough to take care of. Or not, I guess. Whatever. Delete. What? I can't hear, sorry. Yeah, that's what I was double checking. Okay, add 5, sorry, add 6 to this and we get the right answer. On the other hand, with our equation over here, let's go ahead and see now. Now we can just simply instead comment this out. And we can instead do our equation over here, which was num people minus 1 times, and you have to do times here. You can't just put 2 parentheses next to each other and expect them to multiply. Num underscore people, just wait a second please, divide by 2. If I do 6 people, that should give us, 6 people gives us 10. 6 people gives us 10. So let's see. N minus 1, n times, it's n times n plus 1. Sorry, it's n times n plus 1, so it would be, my bad, mismemorized the equation. There we go. That's the issue when you memorize things and don't look them up. 15 minus 1 for your own handshake. There we go. So, in short, with 200 people in the classroom, we would need about 19,000, almost 20,000 handshakes to go around. So, yeah. Now, all right. So, have a good weekend. If you have any questions, please send me an email. Let me make sure that I've got time.